Today we're going to talk about some other indeterminate forms of limits. When we first started working with limits, we tried factoring numerators and canceling with the denominator so that we didn't end up with 0 in the denominator, like on page 466. And then another thing we tried was we would divide every term in the numerator and the denominator by the variable that had the highest exponent, and that was to try to get a constant in the denominator so that again we didn't have 0 or infinity in the denominator. Well, neither one of those things will work on the forms that we're going to look at today, so we're going to try to get them to a form that we can use L'Hopital's rule on. Remember, L'Hopital's rule said that we can take the derivative of the numerator, take the derivative of the denominator, and as long as we end up with an indeterminate form, we can keep doing that until we can get an answer for the limit or determine that the limit doesn't exist. Alright, so 91.1 says to take the limit as x approaches 0 of x times the cosecant of x. Now if we just plug in 0 here, x would be 0, and as x approaches 0, the cosecant of x goes to positive infinity. So that's not any of our indeterminate forms. So what we can do, however, is because we can rewrite cosecant as 1 over sine of x, that might give us a form that we could actually work with. So let's look at that. So that's 0 over the sine of 0 is 0, and that is an indeterminate form. So that allows us to use L'Hopital's rule. So then we'll take the limit as x approaches 0. Now the derivative of x is 1, and the derivative of sine of x, is cosine of x. And now plug in 0. So that's 1 over cosine of 0 is 1, which is equal to 1. Alright, so then we move to 91.2 on page 467, which says to take the limit as x approaches infinity of e to the negative x ln of x. And again, if we let x go to infinity, then this is going to be 1 over e to infinity, which is 1 over a huge number. So that becomes 0, and then ln of infinity would be infinity. That's not an indeterminate form. However, this with a negative exponent indicates that e could be written in the denominator with the positive exponent, leaving ln of x in the numerator. So we take the limit as x approaches infinity. So now we get infinity over infinity, and that's an indeterminate form. So we'll take, use L'Hopital's rule. So the derivative of ln of x is 1 over x, and the derivative of e to the x is e to the x, which gives us 1 over x e to the x. So if we take the limit as x goes to infinity of that, we'll get 1 over infinity, and 1 over infinity is 1 divided by a huge number is 0. Okay, next, also on page 467, 91.3 says to take the limit as x approaches 0 of 1 over x minus 1 over sine x. Okay, so let's look at that. See, 1 over 1 divided by 0, typically when you look at that graph, it goes to positive infinity, minus 1 over sine of 0. Well, sine of 0 is 0, so that would be, also would be infinity. So that's not really telling us anything either. So let's just see if we could add these two fractions together, see what we would get. Limit as x approaches 0 of x sine of x would be sine x minus x. Okay. So then, let's see, that would be 0 minus 0, and down here would be 0. So that's 0 over 0, which is an indeterminate form, which means we can use L'Hopital's. So then that would be the derivative of sine of x is cosine of x minus 1 over, we have to use the product rule here, so 1d2 plus 2d1. Now again we'll plug in 0. So cosine of 0 is 1, so that's 1 minus 1 over, this becomes 0, plus sine of 0 is 0, so that's 0 over 0 again. So we use L'Hopital's rule again. So the limit as x approaches 0 of the derivative of cosine of x would be negative sine of x. Derivative of negative 1 would be 0. And in the denominator, again, product rule, so 1d2 would be minus x sine of x plus cosine of x. And plugging in 0, we would get 0 over 0 plus 1. And 0 over 1 is, messed that up. I forgot the second part of the product rule here. Sorry, guys. That was 1d2 plus 2d1, and then plus derivative of sine of x. So it's 0 plus 1 plus 1. So it's 0 over 2, which is 0. So that, in that case, we had to use L'Hopital's rule twice. All right. The next two are going to involve using left and right hand limits. So 91.4 says to take the limit as x approaches 0 from the positive side of 1 over x minus 1 over square root of x. Now if you think about that, this 1 over x that we just said, that goes to infinity. And again, 1 divided by square root of x will be the same thing, just a less steep curve. So that doesn't tell us anything. So let's get a common denominator. What would the common denominator be for these two? It would be x, right? So x goes into x, that stays the same, minus square root of x goes into x how many times? Square root of x times 1 is that. And then plug in 0. Now think of it coming from the positive side. So from the positive side, this would be 1 minus, that's going to 0, so that would be 1. And this actually would go to infinity when we divide by it. So 1 divided by, actually, sorry, this goes to 0 because x is going to 0. And 1 divided by 0, we know, goes up like that. So that would be infinity. And if you look at the graph of the original function, it actually does go like this. And anytime you want to verify if you are in doubt of what a limit is doing, you can always look at the graph. It should agree with whatever you show algebraically to be the limit. Okay, one more. This is on page 468. 91.5 says, take the limit as x approaches 0 of minus 1 over x minus cosecant of x. Now in this case, what we're going to do is we're going to think about the right hand and the left hand limit on this thing. Because remember, by the definition of derivative, the limit only exists if it approaches the same number from both sides. So if we look at approaching 0 from the positive side, then this, because of the negative that's in front, would be negative infinity. And this would be minus infinity. So that's going to be negative infinity. And then let's look at it from the left-hand side. As x approaches 0 from the negative side. So this one would be, this would be a negative, this value would be negative, times this would make it positive infinity. And the same thing would happen here. So this then becomes positive, so the whole thing here becomes positive. So the right-hand limit is negative infinity. The left-hand limit is positive infinity. So what do we know about the limit at x equals 0? That's right. It doesn't exist because it doesn't approach the same thing from both sides. Okay, that's everything for this week. This assignment is not actually due until Tuesday after Easter. And then we have lesson 92 on that Tuesday, work day, and bonus on Wednesday, and then the test will be on Thursday.